this video, you're going to learn how to work with the law of sines and the law of cosines. This is designed to be a complete guide to teach you about how to work with both law of sines and law of cosines. We're going to talk about how to find missing sides, how to find missing angles, and triangles that don't involve a right angle. So when you had a triangle with a right angle, we just used our regular trigonometry, our sine, cosine, tangent. This is different. This is the law of sines, law of cosines. We're also going to talk about some special cases where you could get two triangles or only one triangle, or maybe even no triangle is possible. We're also going to talk about how to completely solve the triangle, meaning find all the sides and all the angles. So let's dive in and start with talking about the law of sines. And when we work with the law of sines, this is the formula that we're going to be working with. It's the sine of angle A over its side opposite, which we call side A, is equal to the ratio sine of angle B over its side opposite, which we call side B. And that's equal to the ratio sine of angle C over its side opposite, which we call side C. Now, when you work with the law of sines, you only need to use two of these ratios to form a proportion. So what you want to notice is that we use a capital letter for the angles, and we use a lowercase letter for the sides. If we talk about this as angle A, then across from angle A we call side A. And you're just trying to find a pair. So what I mean by that is, let's look at example 1. I like to think about the angle and the side opposite as a pair. So here I can see, here's angle B and side B. Here's angle C and side C. And notice with those two pairs, we can form a proportion and we only have one unknown quantity. So what we're going to do is we're going to say the sine of 40 degrees over its side opposite, which is 6, equals the sine of 100 degrees over its side opposite, which is B. Now you have to be a little bit careful. Sometimes the number 6 and the letter B look very similar. So I'm just going to circle this B so we know that that's our variable. Now we're going to cross multiply to get rid of the fractions. So that's going to be 6 times sine of 100 equals B times sine of 40. And then if I divide both sides by the sine of 40 degrees, that's going to give us our variable B by itself. Okay, now we're going to go to the calculator. Now make sure when you're working with your calculator that your mode is in degrees, since we're working with degrees. Otherwise you're going to get a different answer. So 6 times sine of 100 divided by the sine of 40. And I'm getting about 9.19. So I'll just put approximately 9.19. And that's this missing side right here. Now sometimes when you're learning about law of sines, your book or your teacher might actually take the reciprocal of all of these ratios. So they might say side A over sine of angle A, side B over sine of angle B. So they're basically just flipping it. I prefer to do it this way. It doesn't really matter. You just don't want to mix and match. So if you either put the sides in the numerator and the sine of the angle in the denominator, or vice versa. Now let's take a look at another example here. Now for number 2, what would you do on this one? Well, you can see we've got 35 degrees and we're looking for the side across from that angle. So let's think of these as like a pair. I sometimes like to circle them. And then over here we've got 20 degrees, okay, and we don't know the side opposite, okay, so that means we have too many variables, right? Well, what do? Well, in this case, we notice we have these two angles, so we can add them up and subtract from 180 to find that missing angle. So let's go ahead and do that. So this comes out to 55 degrees. 180 minus 55 is 125 degrees, right? So now look what we have. We have this angle E and its side opposite 8. So we've got a pair, and we've got a pair, and we only have one unknown. So that's the key. So let's write this out. We've got the sine of 35 degrees over its side opposite, which is side D, equals the sine of 125 degrees over its side opposite, which is 8. Now we're going to cross multiply to get rid of our fractions, so you know the cross product property. So this is going to be D times the sine of 125 degrees equals this diagonal multiplied together, 8 times the sine of 35 degrees. Now we'll just divide both sides by sine of 125 to get our variable D by itself. Whatever you do to the left, you want to do to the right. And now we're going to go to our calculator. So let's see, we've got 8 sine of 35 divided by the sine of 125. Okay, so this is coming out to approximately 5.60, and that's the length of this missing side. Let's take a look at the next example. Okay, in example number 3 now we're solving for the missing angle. In example 1 and example 2 we were solving for the missing side. So this is a little bit different type of problem. But notice what we have here. We have a pair. We have angle G, which is 42 degrees, over its side opposite, which is 10. And we've got this angle I over its side opposite, which is 12. So let's go ahead and make our proportion using our law of sines. And we're going to say the sine of 42 degrees over 10, that ratio is equal to the sine of angle I over its side opposite, which is 12. Now what I'm going to do here is I'm going to try to get this sine of I by itself by doing the opposite, multiplying both sides by 12. Okay, and now what we're going to do is to solve for I, we're going to take the sine inverse of both sides. So I is equal to the sine inverse of this whole quantity here. So 12 times the sine of 42 degrees over 10. So let's go to the calculator. Let's see what that comes out to. We've got 12, and you can do this in steps if you want. 12 times sine of 42 divided by 10, and then I'm going to take the sine inverse of that previous answer. So I'm getting 53, approximately 53.41 degrees. So that is the measure of angle I. Now, in example number 4, let's look at this one. Now we're switching gears to the law of cosines. And when we talk about the law of cosines, let's pretend like we're going to do the law of sines. Like say, for example, if I said, here's an angle, and I'm solving for the side opposite. But then I'd have to know this angle and this side opposite, or this angle and this side opposite. Basically, you only want to have one unknown. So if I have two unknowns, law of sines is not going to work where you use the angle and the side opposite as a pair like that. So sometimes students say, well, how do I know when to use law of sines or law of cosines? Now here's an easy way to remember. The only time you really have to use law of cosines is when they just give you either three sides, side, 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 or side, angle, side. What do I mean by that? So if they just gave us three side lengths and nothing else, you'd have to use law of cosines to start off with. If they give you side, angle, side, see where the angle is in between two sides, then again, you're going to have to use the law of cosines to start off with. So that's what we're faced with here is a side, angle, side. So let's go ahead and do the law of cosines. Now, when you look at the law of cosines, there's three different forms of the equation you might notice in your textbook or that your teacher might show you. They'll say c squared equals a squared plus b squared minus 2ab cosine c, or b squared equals a squared plus c squared minus 2ac cosine b. It gets a little bit confusing, but I want you to kind of recognize a couple patterns here. One is that, see, if you're solving for side c, okay, this is angle C over here. So what I think of is that they're across from each other in the diagram, angle C and side C, and they're across from each other in the formula. Then the other two variables, A and B, those are the sides that make up that angle C. Like look over here. So for example, if we have side B and angle B, they're across from each other in the triangle, they're across from each other in the formula. And if we're working with the angle B or side B, then the other two variables here, A and C, are the two sides that make up that angle B. Same thing here, you've got side A and angle A, they're across from each other in the triangle, across from each other in the formula. The other two variables B and C are the two sides that make up the angle. So you can extrapolate that and make kind of like a generic law of cosines formula, which you might think about as this right here, where it's the side squared, we'll just call this x squared, okay, is across from our angle x. Okay, and then the other two sides, side 1 and side 2, that make up that angle, go here. Okay, so you might want to generalize and think about it like that. But going over to this problem right here, using our general formula here, we're solving for side j, that's over here side x. We're going to say j squared is equal to side 1 squared plus side 2 squared. These are the two sides that make up our angle, so that's going to be 8 squared plus 10 squared minus 2 times the two sides multiplied together, 8 times 10, times the cosine of the angle in between those two sides, which is 60 degrees. Now, this is j squared. We just want to solve for side j. So what we're going to have to do is we're going to have to take the square root of both sides. The square and the square root cancel, and we get our side j. Now, you can do this in steps if you want. Like I might put all this in my calculator and then take the square root of that answer. So let's see, we've got 8 squared, which is 64, plus 10 squared, which is 100, minus 2 times 8 times 10 times the cosine of 60. Again, make sure your calculator is in degrees. And then we're going to take the square root of that answer. So I'm getting about 9.17. So approximately 9.17 is the length of side J. Let's take a look at some more law of cosines examples. Okay, let's take a look at example number 5. Now, notice in example number 5, we're given 3 sides, so side, side, side. And remember, when we have side, 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 or side, angle, side, we have to use our law of cosines. And what's interesting about this problem as opposed to the last one is we're solving for the missing angle. So we're going to go ahead and use our generic law of cosines formula, but we're going to be solving here for angle x. We know side x, which is the side across. So we're going to start off with 7 squared equals 5 squared plus 6 squared. Those are the two sides that make up our angle, minus 2 times those two same sides again, 5 and 6, and then the cosine of, I'll just call this angle n here, or in our formula here, this is like our angle x. Okay, now what's interesting here is we have to get this cosine n by itself. I'll just circle it on one side of our equation, and then we'll have to take the cosine inverse to solve for angle n. So whenever you're solving for the missing angle, you're going to have to do the inverse trig function. So let's do this in steps. 7 squared is 49, 5 squared is 25, 6 squared is 36, 2 times 5 is 10, times 6 is 60, cosine angle n. 25 plus 36 is 61, and what I'm going to do is I'm going to take 49 minus 61. So we'll just subtract 61 from both sides. That's giving us a negative 12 equals negative 60 cosine angle n. Again, we're trying to get cosine n by itself, so we're going to divide both sides by negative 60. That comes out to 1/5, or 0.2. And now we're going to take the cosine inverse of both sides to get angle n by itself. So n is equal to the cosine inverse of 0.2. Let's go to the calculator, see what that angle comes out to. You might have to press your second key. And let's see, 0.2. Okay, I'm getting 78.46 approximately. 78.46 degrees, and that's our missing angle n. Now let's take a look at number 6. Okay, so for number 6, we're solving for this missing angle again, just like in number 5. But now we're starting to get into some what we call kind of like ambiguous cases, or some cases where maybe there's no possible answer. And again, when we're given 3 sides, side, 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 or side, angle, side, we think about law of cosines. But what's interesting about this triangle is you see how 5 and 6 only add up to 11. So 5 plus 6 is not greater than 12. There's something called the triangle inequality theorem, which basically means that any 2 sides have to add up to more than the third side. Otherwise, there's no triangle possible. Now, you might be saying, Mario, what are you talking about? So say this side here is 12. Imagine if we really drew this to scale, because this is anybody can draw a triangle and throw numbers on the sides. But in reality, right, say for example, if this was 6 and this is 5, even if I rotate this side down and this side down, you see how there's like a 1 unit gap there? It's like a drawbridge. It's not going to be able to reach, it's too short, those 2 sides. So these 2 sides have to add up to more than the third side, otherwise no triangle is possible. Now, you might be saying, what happens if I don't notice that? Well, you can go ahead and do the law of cosines just like we did here in this last problem, number 5. But when you go to solve for this angle, you get an error on your calculator and you'll say, what's going on? And then you can go back and say, oh, I missed the fact that, it didn't satisfy the triangle inequality theorem. Okay, so for this one, no triangle possible, not possible. Can't be drawn that way. So number 7 now, what do we think about this one? Okay, now this one is also kind of like a special case. And I didn't want to throw this all at you at the very beginning about what we call the ambiguous case, but we're going to start getting into what's called the ambiguous case. And this is called the side-side angle condition. Okay, and what does a side-side angle condition mean? It means that there's the potential for 2 triangles, 1 triangle, or no triangle. And so see how as you go around the triangle, side, side, angle, okay, or you could do angle, side, side. that's when you have the potential for 2, 1, or no triangles. But what's interesting about this triangle, when this angle is obtuse, meaning more than 90, you want to make sure that the side across from that obtuse angle is longer than the side adjacent or next to that angle. So in a triangle, you might remember this from geometry, the longest side is always across from the largest angle. The smallest side is across from the smallest angle. The medium side is across from the medium angle, right? So in this case, there's no triangle possible. Now you might try to do the law of sines because you can see here's an angle and a side opposite, here's an angle and a side opposite. You say, okay, I've got two pairs. Let me do my law of sines. Again, you're going to go to the calculator and you're going to get an error. And so then you might be saying, why am I getting an error? Because you can't really draw this triangle. If we were to draw it more to real life proportions, say this is 9, this is 8, it's like it doesn't reach, you know. Let's take a look at a few more examples. Okay, for number 8, we're going to dive deeper into this ambiguous case situation. So remember, ambiguous cases when they give us side angle. So let's just write that down. So before you dive into a problem, just always look at the triangle and just say, am I given side angle? If I am, just kind of pause for a minute and say, let me analyze this and see if there's 1, 2, or no triangles possible. How do you actually go about doing this? What you want to do is you want to drop an altitude. Altitude means like the height of the triangle. Let's just call this h, okay, for the height. Let's figure out what this height is. So you can see we have this right triangle. You're familiar with your SOHCAHTOA from your right triangle trigonometry. So we're going to say the sine of 30 equals the opposite side over the hypotenuse. So let's calculate that. So sine of 30 equals opposite over hypotenuse. Multiply both sides by 10. And sine of 30 we know is a half times 10 is 5, or you can do that on the calculator. Okay, so you see how this height equals 5? Okay, now when you have an acute angle like this, or angle that's less than 90 and the side angle condition, you look at this side across from that acute angle. If this side, okay, is shorter than this side, like imagine for example, let's change this instead of being 6. Let's say that this was 4. Now if I was to draw that, okay, to scale, you see the problem here with 4? If I rotate this, it's going to be too short. It's like it's not going to reach the other side. That means there's no triangle possible. You can stop right there. You don't have to do any calculation. So it's like a time saver. Imagine if this side here wasn't 4. Say if it was like 5. Well, let's draw that to scale. So now if it's 5, you can see when you rotate it, it's going to just barely touch this opposite side. That means you're going to have a right triangle, so exactly one triangle, right? What happens if this side here, let's go back to the original problem as I drew it. Let's say that this side was 6. Now when this side across from the acute angle is in between the altitude and the side adjacent, see how this is 5 and 10? So a 6 is in between 5 and 10. That means there's 2 triangles possible. Why 2 triangles possible? Well, because we don't know what angle B is, which means that this can act like a hinge. I could actually rotate the side like this. And you can see we're getting this triangle possible or this triangle over here possible. Okay, and then there's one other scenario, and that's where this side here is longer than this side here. So say, for example, if this was like 16, if it was actually 16, it would be like way over here. If I go to rotate it, it's not going to intersect this other side. It's going to like, there's only going to be one triangle possible. So did you follow that? So let's do that again. So if you have a side angle condition, the side across from the acute angle, if it's shorter than the altitude, no triangle possible. If it's equal to the altitude, it's a right triangle. If this side is in between the altitude and the side adjacent, you get 2 triangles. That's what we're going to do right now in just a minute. And if this side here is longer than the side adjacent, okay, that means it can only go this way. You can't rotate it over here. It's only going to be one triangle possible. Okay, so now in this 2 triangle possible scenario, let's draw our 2 triangles. So we have the original triangle, which is this one right here, okay, and we have this little triangle over here. So let me draw the little triangle. Kind of looks something like this. Okay, so this is still going to be 30 degrees. This is still going to be 10. This is still going to be angle A, B, and C, and this side over here is still going to be 6. So then the question is what should we do first? Say we want to solve this triangle. Maybe we want to find all the angles and all the sides. Well, because I have an angle and a side opposite, and I don't have this angle, but I have this side opposite, we have to solve for angle C. So let's do that. Let's say the sine of angle C over its side opposite 10 is equal to the sine of 30 over its side opposite 6. Okay, so we're going to multiply both sides by 10 to get the sine of C by itself, and then we're going to take the sine inverse of this quantity to get C. So let's do that. So sine of 30 is a half times 10 is 5, so that's 5/6, and we're going to take the sine inverse of 5/6. Okay, that's coming out to, I'm going to just round to the 10th to keep this a little bit simpler on this problem. So 56.4 degrees. Now see how this is 56.4 degrees right here? But remember when we took this side and we rotated it, see like this? If this is 6 and this is 6, what kind of a triangle is that where the two sides are congruent? It's an isosceles triangle. What do you know about the base angles of an isosceles triangle? They're congruent. So if this is 56.4, this is 56.4, how much is this angle next to the 56.4 degree angle? That's going to be 180 minus 56.4, which is 123.6 degrees. See, so this, remember this little triangle here? That's our other possible triangle that could be drawn given that limited information of side-side angle. So this angle here was just 180 minus the 56.4. Now notice what we have here. We've got this angle, this angle. If I want to find angle B here, all I have to do is add these up and subtract from 180. So let's do that. 180 minus 30 minus 56.4. So this is coming out to 93.6. This angle over here, we're going to subtract from 180. So 180 minus 30 minus 123.6 is 26.4. Okay, so that's that angle. And now all we're left to solve for is this side here, B, across from angle B. Same thing here, this side B across from angle B. So how can we do that? Now, when I do these problems, I try to go back and use the original values if at all possible, because those are exact, whereas 56.4, that's rounded. So to be a little bit more accurate, I'm going to say sine of 30 over 6 is equal to sine of 93.6 over its side opposite, which is side B. We can do the same thing for this triangle here. We could do sine of 30 over 6 is equal to sine of 26.4 over side B. So let's go ahead and solve both of these. So I'm going to cross multiply. So that gives us 6 sine of 93.6 equals B times the sine of 30. Divide both sides by sine of 30. And that gives us the side B for this triangle. So let's do that. 6 sine of 93.6 divided by sine of 30. Okay, it's coming out to 11, well, it's 12.0. We're going to round to the nearest tenth on this one. So 12.0 for this side right here. And then if we do this problem, 6 times the sine of 26.4 is equal to B times sine of 30. Divide both sides by sine of 30 to get B by itself. And let's see what that comes out to. Okay, 5.3 approximately. So that's this side right here. So what we did in this problem was not only determine whether there was 1, 2, or no triangles. Because there was 2 triangles, we actually split it up into the 2 triangles, and we solved each triangle individually to find all the missing angles, all the missing sides. We're going to do some more examples, but I just want to point out to you that there was 2 side Bs, there was 2 angle Cs, and there was 2 angle Bs. So 2 different triangles. Let's take a look at the next example. Okay, for number 9, why don't you try number 9 on your own if you can. What we're going to do for A, B, and C is we're going to determine are there 1 triangle, 2 triangles, or no triangles possible. So see if you can do this. So for letter A, 9A, what do you think? 1 triangle, 2 triangle, or no triangles? Well, notice we have the side-side angle ambiguous case, or the side-side angle condition. So what I like to do is I like to drop an altitude, like so, and now we have a right triangle. We can find out what that height is. So that height is Sine of 41 equals h over 8. Multiply both sides by 8. That's going to be 8 times the sine of 41 degrees. That comes out to 5.2. Okay, now what's interesting is remember when the side across from the acute angle is longer than the side adjacent, there's only one triangle possible. So we really didn't even need to find the altitude on this particular problem because the side opposite the acute angle is longer than the side adjacent. So we're just going to say one triangle possible on this, and we don't need to solve it for this problem. But for letter B now, what do you think? One triangle, two triangle, or no triangle possible? Well, if I was going to do this problem, I would drop an altitude, and I would find out what this height is. So I'd say sine of 26 equals h over 7. Multiply both sides by 7, so that's going to be 7 times the sine of 26 degrees. That comes out to 3.1. Okay, so let's write that down, 3.1. Now, notice that the side across from the 26 degrees is shorter than the altitude. See, if I was really to draw this to scale, 3 is only going to be like this. When I go to rotate it, it's not going to reach since the height is 3.1. So in this case, there's no triangle possible. And then for letter C, what do you think on this one? Two triangles, one triangle, or no triangle possible? If I was going to do this, again, I would drop an altitude, solve for the height. So sine of 35, let's write this one down, equals opposite over hypotenuse, multiply both sides by 6. So that comes out to 6 sine of 35, 3.4. Now notice 5, the side across from the acute angle, is in between the altitude and the side adjacent. That means we can actually rotate this like that to form a second triangle. So in this case, there's actually two triangles possible. Okay, so now let's go to number 10. We're going to talk about how, again, to solve the entire triangle. So see if you can pause the video and try this one. Find all the angles, all the missing sides, basically find everything. So remember, a triangle is made up of 3 angles, 3 sides. In this case, they're giving us 3 pieces of information. We have to find the other 3 missing pieces. So how would you do this one? First thing I would do is I would look at the information that I'm given. I'm given a side, angle, side. See the angle in between the 2 sides? That tells me law of cosines I have to start off with. And I'm going to solve for the side across, side W. Now you can use the generic form we've been talking about here, which should be this side here squared is equal to the 2 other sides that make up this angle, so 7 squared plus 6 squared minus 2 times 7 times 6 times the cosine of 43 degrees. Take the square root of both sides to get W by itself, and then let's see what that comes out to. So 7 squared is 49, 6 squared is 36, minus 2 times 7 times 6 times the cosine of 43, and then take the square root of that answer. I'm getting about 4.85, so approximately 4.85 is this missing side. Now, notice we have an angle and a side opposite. We can think of that as a pair. And let's say we want to solve for angle y. We have a side and we just have this missing angle. So let's go ahead and do our law of sines. Notice when you do the law of cosines first, you only have to do it at most one time, and then you can switch over to law of sines, which is a lot simpler and quicker. So sine of angle y over 7 equals the sine of 43 over 4.85. Multiply both sides by 7 to get sine of y by itself, and then take the sine inverse of that answer. So let's go ahead and do that. So sine of 43 times 7 divided by 4.85. Take the sine inverse of that answer. So it's coming out to approximately 79.84 degrees. Okay, now we just have to solve for angle x up here, and you can see that these 2 angles plus this third angle have to add up to 180. So if we do 180 minus these 2 angles, we can find that missing angle x. Let's see what that comes out to. Looks like we're getting 57.16 degrees, and you solve the triangle. You found all the angles and all the sides. Let's take a look at 2 more examples where you're solving the entire triangle. See if you can try these on your own. Okay, see if you can pause the video and try number 11. So we're going to solve the entire triangle, find all the missing sides and all the missing angles. So how would you do this one? Well, if I was going to do it, I would kind of look at the information that we're given here. It looks like we're given side, side, side. So remember, when it's side, 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 you're going to want to start off with law of cosines, or side angle side, law of cosines. So in this case, we're going to have to start with law of cosines. And oftentimes teachers will say, well, go ahead and start by solving for the angle that's across from the longest side. So we'll start off by solving for angle I. Now you might want to analyze the triangle inequality theorem to make sure that these two sides add up to more than this side. So that's 15, or these two sides add up more to this side, or these two sides add up to more than this side. So any two sides have to add up to more than the third side. In this case, it looks like it satisfies that triangle inequality theorem. So using the law of cosines, let's start with this generic formula. We're going to solve for angle I. So we're going to say the side across from angle I, that's over here x, so that's going to be 11 squared, equals the two sides that make up the angle, so that's going to be 6 squared plus 9 squared, minus 2 times those same two sides, 6 times 9, times the cosine of angle I. So our goal is to get cosine of I by itself, so that we can then take the cosine inverse and solve for the angle I. Okay, so let's go ahead and simplify a little bit. 11 squared is 121, 6 squared is 36, 9 squared is 81, 6 times 9 is 54, times 2 is 108. Some students mistakenly try to subtract these two numbers, but you want to think of this as a group. So I would add these together and subtract from 121. So let's see what that is. 36 plus 81 is 117. And if we subtract 117 from both sides, we get 4. Now we can divide, oops, this is angle I here, cosine of angle I. So we can divide both sides by negative 108 and take the cosine inverse. So I is equal to the cosine inverse of negative 4 over 108. So let's see what that comes out to. 92.12. So I equals 92.12 degrees. Now we need to solve for angle N or angle W. So let's go ahead and solve for angle W. So we'll just do the sine of W over its side opposite, which is 9, is equal to the sine of 92.12 over its side opposite, which is 11. So notice we only did the law of cosines once, then we can switch to the law of sines. We'll go ahead and multiply both sides by 9. And then to find W, we're going to take the sine inverse. So W equals the sine inverse of this whole quantity. So let's go ahead and do that. Sine of 92.12 times 9 divided by 11. Take the sine inverse. And we're getting 54.85. And that's for this angle. And then we know all the angles in a triangle add up to 180. So we can take 180 minus 92.12 minus the 54.85. And it looks like for angle N, we're getting 33.03 degrees. And we solved the triangle, all the sides, all the angles. Let's do one last example. See if you can do this one on your own. Okay, see if you can pause the video and do this last one on your own, example number 12. What do you think about this one? Well, if I was going to do it, I would look at it and I'd notice that they're giving a side-side angle. That's that ambiguous case that we've been talking about here and there. And side-side angle, we can see that the side opposite acute angle is not longer than the side adjacent. So if this was longer, if this was, let's say, like 12 or something, there would only be one triangle possible. So to analyze this, let's go ahead and drop an altitude, this height here. And let's figure out what that height is. So the sine of 54 degrees equals opposite over hypotenuse, multiply both sides by 9 to get h by itself, and let's see what 9 times the sine of 54 is. That's 7.3. Okay, now notice that this side 8 is in between the altitude and the side adjacent. That means that we can actually rotate this to form a second triangle. Let's draw the two triangles so we can see them clearly here. We've got this triangle, which is like our original triangle, MAT. Okay, and then let's see, this is 54 degrees, and this is 9, and this is 8. And then when we rotate it, we get this little small triangle, kind of like this. Okay, and this is still going to be MAT. t, this is still going to be 54 degrees, this is still going to be 9, this is still going to be 8. Okay, so what we need to do is we need to solve for angle t over here, because we have 54 and 8, that's a pair, t and 9, that's a pair. So angle and the side opposite form a pair. We can do our law of sines. So let's start off by using this triangle here. We'll say sine of 54 over 8 is equal to the sine of angle t over 9. Multiply both sides by 9, and then we'll take the sine inverse of this whole quantity. So let's see what that is. So 9 sine of 54 divided by 8, take the sine inverse. That comes out, so I'm going to round to the nearest tenth. Let's just do the nearest tenth on this. So this t comes out to approximately 65.5 degrees. 65.5 degrees. Now remember, if this angle is 65.5, when we rotate it, if this side here is 8, this side here is 8, and if it's an isosceles triangle, the base angles are congruent, which means that this is 65.5. So that angle next to it right here, which corresponds to this angle right here, is going to be 180 minus 65.5. So that's 114.5 degrees. Okay, now when we have two angles in a triangle, we can find the missing third angle by subtracting from 180. So 180 minus 54 minus 65.5 gives us 60.5 degrees. And this angle up here, we'll do 180 minus 54 minus 114.5, which gives us 11.5. Okay, now all we have to do is solve for side A in both these triangles. So over here, let's do sine of 54 over 8. Notice I'm going back to those original numbers because they're not rounded, equals the sine of 60.5 over side A. And then we'll do the same thing over here. We'll do the sine of 54 over 8 is equal to the sine of 11.5 degrees over this side A. Okay, so let's go ahead and solve. So we're going to cross multiply. So that's 8 times the sine of 60.5 equals A times the sine of 54. Divide both sides by sine of 54 to get A by itself. And let's see what that comes out to. So 8 sine 60.5 divided by sine of 54. We're getting 8.6 for this triangle. And then over here for this smaller triangle, we'll cross multiply. So A times the sine of 54 equals 8 times the sine of 11.5. Divide both sides by the sine of 54. And let's see what that comes out to. Whoops. Divided by this, oops, let me try that again. I made a little mistake here. So when I was typing 8 sine of 11.5 divided by the sine of 54, okay, I'm getting about 1.97, which rounds to 2.0 if we're rounding to the nearest tenth. So this is 2.0. And you solved the triangle, actually both triangles that were possible, and you got it. So great job if you're able to follow all the topics in this comprehensive, complete guide to law of sines and law of cosines. If you want more practice, follow me over to a previous video I did talking about law of sines and law of cosines right there, and I'll see you over in that video.